I'd rather the blackboards be taller and like,
It is.
yeah, I'd rather them be more square.
Yeah, the microphone's on. Can you tell?
That's fair. It would be nice if we were like,
Yeah, I think it's on.
maybe like all the blackboards being angled, so if you
All
look.
right, welcome back, everyone, for the afternoon session. Let's get started.
Students, I need some water. Well, this is my second lecture. The first lecture I talked about Galois representations, and in this lecture I'm going to introduce eigenvarieties, but I put a question mark there because I'm not sure how much the formal definition of an eigenvariety or something you will see. But it's certainly the circle of ideas is what I'm going to try to communicate. And I will mention that in French they don't use the word eigenvariety; they say varieties de Hecke. Hecke eigenvariety is another term that you might hear people use to really emphasize that the varieties, they're geometric spaces that are related to Hecke. Hecke what? Hecke eigenforms, and that's where the eigen comes from. Okay. So I'm going to start where I left off, and I'm going to spend most of the talk on the following results, which is also serving to review a little bit what I talked about last time. So E is going to be the elliptic curve, y squared plus y equals x cubed minus x squared minus 10x 20. This is this curve x naught 11 from the last talk, and it has good reduction at L different than 11. And there's a theorem, p-adic. So the following. So to look at curve corresponds to a weight to modular form, and the theorem is about other weights beyond 2, but it starts with an integer that's at least 2, and also congruent to 2 modulo 10. 10 here is 11 minus 1. Okay, so that's where the number 10 is coming from. So that there exists the Galois representation. We're okay. So there's a representation on the absolute Galois group valued in 2 by 2 matrices over the 11 integers, which is continuous and unramified away from 11. Okay, just like the Tate model of this elliptic curve. Okay, such that point 1, all of the row k's are going to be congruent to row 2, which is row E, modulo the prime 11. So for each k in an arithmetic progression, I'm going to construct a Galois representation that's going to be congruent to my row E. So these are all defining points in this deformation space that I talked about last time. The deformation space of the mod p Galois representation. Every k is going to be a new point. Last time I did it for k is 12. Right? K is 12. You're going to get the delta, the row delta that I talked about in the last lecture. Actually, I can write that here. Point 2 is that row k is associated with a weight k eigenform Fk. Okay, and let me just say, remind you, because I stated the theorem so abstractly, it might be less concrete than you imagine. Here, that's going to mean that the determinant of row k is the k minus first power of the cyclotomic character. Okay, in the presence of an Nevinson character or a central character like an Oberon stuff, there might also be some other Dirichlet character here, but in this setting there won't be. And the trace of row k on a previous element at L is going to be AL of this eigenform at k. for L different than 11. That's what it means for rho k to have been associated with the eigenform. And yeah, I said there's a lot of it, I mean, it's right. F12 is going to end up being the delta function. And third, yeah,
I just have a question needs ALs were both the coefficients of some modular form and also counting points on the elliptic curve, right?
so the AL for a modular form is the Q to the L coefficient of its Q series.
Okay.
When that modular form arises from the elliptic curve, separately, that AL is counting points on the elliptic curve mod L.
Okay.
But for a general modular form, there's no such formula. Okay. Yeah, does that answer your question?
Yes. In this case, is this one of the cases where it is counting points in a curve?
Only when K is 2. When K is 2, you're going to get the modular form associated with this elliptic curve. But when K is 12, 22, and so on, it's a higher weight modular form. It is what it is. There's no elliptic curve related to that thing directly.
Okay.
Okay. Mention that again later, like maybe after the talk, and I can explain also there's growth laws for the size of these coefficients in terms of K, and only in weight 2 could it ever be associated with an elliptic curve like this. These numbers are too large and Archimedean size to be associated with elliptic curves. So the third part is a theorem of K. That's a weird thing. Okay, so K goes to AL of Fk, so that takes as input a number K and outputs an algebraic integer. Okay, this is going to be p-adically locally analytic in the sense of the talks we'll get to the afternoon. P-adically locally analytic in the variable K for each L. Okay, and even jointly. Somehow they'll all have the same radius of convergence. It's not L by L, I get a different radius of local analyticity, it's all of them at once. Okay, and like I said, this is the way I've stated this is a theorem of Kita. It's very special to the situation of fixing this elliptic curve and the congruence mod 10 and all these things. This is a much more general theorem, but I thought I would say it this way. And let me also say, point 3 is significantly more hard than point 1 and 2, I think. And what I'm going to do, I'm going to basically set it up so that I can prove 1 and 2, and then explain how 3 works, building on that idea. But I think the idea for 1 and 2 is really the origin of the idea of the eigenvariety, and part 3 is the realization of that idea. You have another question? Yeah.
Yeah. For point number 3, if we're thinking p-adic locally analytic, are we allowing K to be a p-adic number?
So what it's saying is that there is a locally analytic function on the p-adic integers that when you specialize to an integer K will recover the value AL of Fk.
Oh, okay.
Yeah, most definitely. And then you could even imagine that then there's some function AL of kappa where kappa is a p-adic number, and there's some Q expansion, and then Q expansion is some sort of p-adic modular form, and this is really the heart of what an eigenvariety is. But that's maybe for more lectures. Okay. So now, cohomologies in action or with action. So this came up at the very end of the last talk, and it's perfect the way the timing worked. Let me just mention. So for those of you who are going to go into the p-adic theory and you're looking for references for this kind of thing, let me mention the paper of David Hansen that begins with the word universal and ends with eigenvarieties or something like that. It was published in the Krell journal in the past decade, where he writes all the formulas, I'm about to say. There's no really arguments there, but it's like a good reference for p-adic people in understanding these questions of cohomology. And I'm going to set it up similar to Raghuram's talk. We're going to start with delta, which you should think of as gamma naught 11. Sorry, gamma, which should be gamma naught 11 or any other congruent subgroup. And inside that, I'm going to assume that I have something called delta. Delta is not so good. All the deltas after here are not going to be a Ramanujan function. Ramanujan function are going to be something else. And these are all going to live inside GL2 plus a Q, so 2 by 2 matrices with positive determinant over the rationals. And I'm gonna assume that M is a left delta module. Let me just say that delta being all of GL2 plus is good. That's an example you could think of. So delta is GL2 plus Q could be the example, but in general, gamma is going to be a group, and this is a group, and delta is not going to quite be a group. It's just going to be closed under multiplication. Okay. Now, there's a delta action. Then on the homomorphisms from the singular chains on the complex upper half plane valued in M. And that, so these are maps from singular chains valued in M, and delta acts on it by the formula of G times B of a chain is G inverse times sigma, where this G inverse means acting by fractional linear transformation on the upper half plane. And here I'm being really careful that I only act by G inverse on the upper half plane. I don't act by G inverse on M, because like I said, delta might not be a group in this setting. So maybe I should actually write this. This is a monoid. This is a group like gamma 0, 11. And of course that's a group. Okay, so there's some action on what is essentially the thing you would start taking if you were trying to compute cohomology with M. You're taking the dual of the singular chains. A lemma. You're going to say that when you take the cohomology of Y gamma, which is just think of it as gamma 0, 11, with coefficients in M, which is as was in Roger Armstrong, except maybe there was an M tilde there to denote a sheaf instead of vector representation. This is the cohomology of the gamma invariance of this action. So you take the hom of the singular chain on H, coefficients in M, and you take the gamma equivariant ones, which is the same as the thing fixed by gamma here, right? Because to be fixed by gamma means that this and this cancel, which is to say that the gamma pop up. Okay, now why is that true? It's true because Rajaram wrote it on the board during a question and answer session after we all left the room. Okay, so this is a basic way of calculating the cohomology, and the beautiful thing is the formulas are so simple somehow. What? That's not your handwriting. Okay, so who wrote this? What's your name? Matt wrote this. So this is Matt's lemma. Matt's lemma. I mean, of course, it's yeah, good. Now, one thing I do want to stress, the action here. You can almost forget about this from the point of view of calculation. What I really want to point out in this action is when you act by these elements of delta, you hit the M. You act on the module that you're touching somehow. Okay. Anyways, this leads to the head action. So assume that G is in delta and gamma G gamma decomposes into right cosets like this. That's an assumption. So that's it won't always happen kind of for some abstract setting. So I just assume that, and in all the examples it will happen. So for instance, I can give you an example. If I take gamma 0p and p001, gamma 0p, this decomposes. P goes from 0 to p minus 1 of pb01. Gamma 0. That's an example of this decomposition. And then you can check that once you have a decomposition like this, there's an operator on the cohomology, sorry, up there. Gamma G gamma phi, I define it to be the sum bi dot phi, and this defines an endomorphism of the cohomology. This is one way of defining Heck operators on cohomology. Using explicitly these things about singular change and representing everything that way. Do you have a question? Are you sure? Okay. And it's a good consistency check. Based on the formulas, you really can check for instance if this is a well-defined endomorphism on the cohomology. Okay. Good. So then next task, I think it's just to make this more concrete, right? Last lecture I was making everything quite concrete, and this is the abstract. So let me unwind part 1 and 2 of this theorem now. So I take the cohomology. Let's say that. I skipped the second, but I'm actually giving you the example. Sorry. So I think in the last lecture, he introduced these symmetric powers, and then they came up again. So let me write down the action. Okay, I'm going to take R to be a non-negative integer, and then MR is going to be the symmetric R power, and I'm going to do something that was not happening in the last lecture. I'm not going to plug in rational or complex coefficients. I'm going to plug in ZP squared. Okay, I want to do things integrally. Here, these are the ZP homogeneous polynomials, ZP linear homogeneous polynomials of degree R in 2 variables x and y. That's the definition. And the action I'm going to use, Maladen told me I could choose my action. So there's different ways of normalizing this action, and I hope it lines up with whatever formulas you want to use later in the week, or you can adjust, is A, B, C, D times a polynomial evaluated on x and y is going to be P of AX plus DY, DX plus DY. Okay, so that's an action you can put on homogeneous polynomials of degree R and x and y, and this action will make sense. So this is a ZP polynomial, so I need to make sure something p-adically integral is happening here. So this will make sense as long as I plug in a 2x2 matrix that, of course, has invertible determinant in Q because I need a GL2 plus a Q. Okay. Somewhat simpler or somewhat more sophisticated, depending on your point of view, I can take MR bar to be MR mod P, which is a sim R of FP squared. So I can take the same modulus, I can use mod P coefficients. And here, what I want to point out is that inside MR bar, there's something I'm going to call WR bar. This is not some standard notation. This is just for the purpose of this talk. And this is going to be the FP span of all the powers of all the monomials that have an X in them. So it's a codimension 1 subspace, right? The homogeneous polynomials are spanned by all the different monomials, and I'm just leaving out y to the r. Then you already know that MR bar has an action of this monoid by the same action, and this monoid will be stable as long as you change your monoid a little bit. Sorry, this representation will be stable as long as you change your monoid a little bit. This is delta 0 p stable, where this are all the matrices A, B, C, D in delta. Where C is divisible by P. So somehow this is like matrices of level 1 almost. They're just all matrices. And this is like putting a gamma zero p condition on the monoid action. And why so? Yeah, well, I mean, you can just calculate this, that as long as C is divisible by P, whenever you plug in something divisible by X, you'll also still be divisible by X. Because this term won't contribute at all mod P. Right, when C is 0, that's not going to change. Okay. Then I have a lemma. So if I look at UP, which I define to be the double cosine operator, which makes sense for this model with this action, right? Because this lies in my W0P. Then it acts on the cohomology of y gamma 0p, WR bar coefficients as 0. So it completely annihilates the WR bar cohomology. And the reason for that, I show you, just so that we have some chance to use some of these formulas. Here's my decomposition that I need to use for the UP operator. But if I look at P(B01) and I multiply by a polynomial, P bar xy, that's going to be P bar 0 bx plus y, which is 0, P bar is in my subspace. You see the P here is like my A, but of course mod P is not there. So I'm just plugging in 0 and 0. So I get 0 here, but then in WR bar I have all X's everywhere, and so okay, I vanish. And so every one of these actions, that's why I emphasize so much that here you really act on the coefficients. Because I don't even care what these translates are, I just annihilate that whole WR bar. Okay, just on the action. Okay, other questions? The stuff can be made kind of this concrete, I think. There's Matt lemma. Let's go back to the meaning of the theorem. What is the meaning of Peter's theorem? So what I'm going to do now is I'm going to take the cohomology at level gamma 0, 11, right? The theorem I wrote is about level 11, so I'm really going to do that now. And I'm going to take my MR, which is with integral coefficients, and I'm going to fix the sign plus minus like in Roger Raum's talk, and that's just, normally there's 2 copies of cusp forms everywhere, and I'm going to fix one of those copies. It doesn't matter which one. And this is going to have an action, not just of kind of this UP operator, but also the unramified Hecke operators. So UR was the notation that we saw in the Peter's talk yesterday, and also the U11 operator. So here, T unramified is going to be the Z11 algebra generated by the Hecke operators different than 11, which you generate exactly the same way that I generated here, except when O is different than 11, there's one more piece of the decomposition that's like 1, 0, 0, L. Okay, so I don't think I need the formula, so I'm not necessarily going to write it down. Okay, so that's the first thing, is this cohomology has a Hecke action, and the Eigenvarieties theory that was explained in Roger Raum's talk is equivariant for this Hecke action as long as I normalize things correctly. I'm not quite sure whether we've normalized everything correctly, but I think it's okay. Up to normalization. So now I define M bar to be the kernel of the map that takes the unramified Hecke algebra plus U11 and maps to F11. I'm going to call this psi bar. And what is psi bar? So psi bar TL is this AL of E, this point counting function for my elliptic curve. And psi bar of U11 is A11 of E, but I want to write it down separately so that I tell you its value. psi bar of U11 is A11 of E is 1. That's something you can figure out like by counting points. And in particular, it's not 0. Okay, so it's a non-zero number model of it. So I have a heck action on the cohomology, and then I take a maximal ideal of the cohomology corresponding to the Hecke eigenvalues associated with my elliptic curve, except only modulo 11. Okay? And now what does Eichler and Shimura theory tell you?
Why are you putting a bar on the ideal?
I'm putting a bar here and a bar here because they're mod. You want the ideal to not have a bar? That's fine, it's not gonna ruin.
It's not in characteristic P, right?
The M bar is not in characteristic Z. In fact, it's the maximal ideal in the characteristic Z. It is Z11 algebra, that's right. The psi bar maps to characteristic Z, so maybe that deserves a bar. Good. So Eichler-Shimura theory explains how Hecke eigensystems or Hecke operators arising from plus forms actually arise in the cohomology. And so the meaning of p to 0, as far as I'm concerned for this talk, parts 1 and 2, is that it's enough to show, or you want, the following statement to be true. When you take the H1 of y gamma 0, 11, MR, you fix the plus minus sign so that you isolate one copy of the cusp form, and then you localize at M. So you localize the algebra at this maximal ideal, localize the model at the maximal ideal of the Hecke algebra, then this should be a free rank 1Z11 model. Okay, and that isomorphism is what I want to show. So this model is some Z11 module, it's some finite Z11 module, and after taking plus minus parts and localizing at M, I want to show that it's free of rank 1. When R is congruent to 0, mod 10. And of course, here I could remind you that R, the R I'm using here, the R that appears in these symmetric powers is like K minus 2. So this came up also in Bergdall's law, and that's why everything here is for 2 mod 10, and that's for 0 mod 10. In any case, if you show this kind of thing, then AL about K will be the TL eigenvalue here. So once you have a free rank 1 thing, the Hecke algebra will preserve it. So you'll get an eigenvalue for each Hecke operator, and that will be the AL. That will give rise to these Galois representations. It will give rise to an honest eigenform, is what I mean to say. Okay. So how do you prove the smiley face statement? Are there any questions while I do that? Maybe you're not sure what something means. It's a tough word, I'll be honest. But if you have a question, put a star next to your paper, and you can ask me later what I really mean by this. If you can't tell by the way I set things up, what I'm going to do now is a trick that where I really start using the specific situation I put myself in to simplify all the calculations. So Peter proved the experiment in great generality. We have to worry a lot about a lot of different technical things that can show up. But for this particular example, I can just state a series of facts. So let me see why that thing is free of rank 1. And the first one is this. So step 1. So the Hecke action mod 11 associated with this whole setup is the one associated with this mod 11 representation. The mod 11 kind of the action on the 11th version of this elliptic curve. And we had this discussion yesterday that action is irreducible. Okay, and what that means is a non-formal statement. And this is that it's both in other situations, that if you look at the cohomology with these MR coefficients, plus minus, you localize the maximal ideal, and you reduce the cohomology mod 11, it's the same as calculating the cohomology mod 11. Isomorphic, the cohomology. Sorry, I don't need any more. It's isomorphic to the cohomology mod 11. So here I've reduced everything. I have to take plus minus parts and put my maximal ideal there. Okay, so that's a consequence of the irreducibility. I mean, in my round plot, there was only H1, and so far you've only seen H1, but in practice, there could be, I guess, H0 that I'm using the open curve. And H0 contains Taka eigensystems, but those Taka eigensystems don't arise from actions that give rise to irreducible Galois actions, they arise from Eisenstein theories. Okay? So there's a step here that you need to understand. Step 2. Let's look at my lemma. So the lemma and the fact that psi bar of U11 is an F11 cross, what did it tell you? Well, if my psi bar, where did it go? Yeah. My psi bar here has a non-zero eigenvalue on U11, and I'm localizing at that ideal. And what that means is that once I localize, I can't be acting by 0 anywhere because I have to be acting by a unit. And so once I localize, the WR bar doesn't contribute at all to the cohomology. The H1 Y gamma 0, 11 MR bar now localized plus minus is isomorphic to the H1 Y gamma 0, 11 MR bar modulo WR bar localized at M taking plus and minus. Okay? And something really remarkable just happened. MR bar has dimension R plus 1. But WR bar has codimension 1 in there. So this is a one-dimensional vector space that I'm acting on. And I've completely reduced this high dimension, possibly high dimensional thing, something with one-dimensional coefficients. And so step 3 is to analyze those one-dimensional coefficients. And you just check that when R is 0 mod 10, MR bar modulo WR bar is nothing but a one-dimensional vector space occurring when R is 0, the weight 2 one-dimensional vector space. And I can tell you the isomorphism, right? So this is generated by Y3R times a scalar. And the scalar says it's just a scalar, right? In degree 0, there's only scalars. And that thing will be equivariant for this delta 0, 11 action. Working at level 11 is really important. And so my smiley face statements, so to check on free of rank 1 here is enough to check on one dimensional here. And all of this tells me that it's enough to check it in weight 0 or weight 2, sorry, that's enough to check it when R is 2. So is true for R is 0, if it only has any R. For the R is 0 case is, I mean, let me just say it's given. Somehow this analysis wouldn't make any sense if I didn't already know that associated with my elliptic curve, there was a unique rank 1 cohomology, like the cohomology class kind of generated a rank 1 object. Okay. Yeah, there's a question, that's fine. Yeah.
Trying to see how to organize WR bar. So what is happening for the finite dimensional representation? It's like you're picking your lowest weight or highest weight vector.
So let me just tell you what it is, a complement of the highest weight vector, but what's happening is these symmetric power representations in characteristic 0 are irreducible representations of GL2. In characteristic P, they're extremely reducible. The only irreducible ones happen when R is at most P minus 1. Okay, and all the irreducibles are twists of those low ones. But until there's some list of them, there's like P squared irreducible in characteristic P. But what I'm doing here, Ragaram, and the question was what's going on with the representation here, is I'm not just looking at the GL2 representation, I'm restricting to the to the upper triangular matrices mod P also. And as a module over the upper triangular matrices, the symmetric powers are completely reducible. And I'm taking kind of the top piece of a full flag, the top non-trivial piece of a full flag, and that's what WR bar is. Okay. So that's an argument, and maybe it took longer than you might be expecting, but maybe as you're reading through research papers and stuff like that, this is the kind of thing you can come back to when things get complicated. Like this is the simplest case of the whole story. Yeah.
So this would hold for, and would something like this hold for any level where this sort of original cohomology at level 0 is one-dimensional? Is that sort of the
Well,
basically just step 1 through 3 go through under the assumption?
so step one only uses the irreducibility of the Galois representation.
Okay.
Step 2 goes through as long as you know that mod 11 you have a unit action. And then step 3 is completely formal analysis of this, except for what's happening in weight 2.
Yeah.
Yeah.
Okay, yeah, that was my question.
But in Bergdall, I mean, the localization, like Gothic M for the initial one doesn't need to be one-dimensional.
Yes.
You can have congruencies at the initial level,
Mhm.
and then that's not kind of working anymore.
You know, Congress is between 2 weight 2 things.
Yeah,
So okay, now I understand the question. I didn't understand that. At first I said that it's R is 0 is given in quotes, and that given is an analysis that you make a finite computation to realize.
Yeah.
Yeah.
There's formulas for that.
Yeah.
somewhere.
Yeah, sorry. Okay.
that's a very difficult thing to do on a computer. Actually, Rob Pollock has done it kind of, but it's very not trivial. I mean, to decide if two forms in the PC are in the same p-adic family, I mean, if they're not congruent, then they're not in the same. So there is a necessary condition to be congruent. But if there are many congruent things, you don't know, like if they're in the same family or there are many families.
Yeah.
So
Well, maybe you're looking, in some sense, is this not asking like, what is it, some modular curve? Right. Sort of-
John put himself in a situation of a single family because by congruence he killed all the other families, right?
Yeah, I think in weight 2 and level gamma 011, there's like 2 cos forms that are degenerated of delta, and there's one isosine series.
Yeah.
And I just know that they're not congruent somehow. Like I could just analyze them. Yeah. That's really what's going on in this given part. In general, there's a reason why he does arguments in his book is longer than this, is what I would say. And actually, okay, I'm not gonna get into that now because it's probably like a 10-minute story. You can ask me about this argument at the end after the talk, and how happy I am. Okay. As long as it's right. So features to highlight. What's going on? Let me walk you through this. By the way, let me back up because it was a little bit much what I did. All I did was show that the cohomology is ranked 1 in each weight kind of congruent to 2 mod 10 or 0 mod 10, depending on how you're measuring it. Then you have to go back through Shimura to get an eigenform, and those are the eigenforms constructed in the theorem. So I didn't do that part explicitly. But there's some features that you want to pay attention to. So I moved from R as congruent to 0 mod 10 to just R as 0, which is the same as going from K as 2 mod 10 to K is 2. That's not to say that I'm making some formal statement here. It's just I did something about moving the weight. Okay. I think we can all agree that that's something I did. Step 2 is I only proved, quote, only, I don't know what that means, only proved a statement on Hecke eigensystems. In the earliest days of questions of p-adic modular forms, the objects that we're being deformed are really Q expansions of modular forms. That is not what I just did. What I did was I produced rank 1 pieces of cohomology that were necessarily stable by Hecke action, and then by some other formal not nonsense, some other formal properties of this Ishimura isomorphism, I produced eigenforms. But all I really did was keep track of Hecke eigensysters. So there's a huge theme in p-adic algebraic number theory in the past 20 or 30 years. It's really thinking only in terms of Hecke algebras and their actions on things like cohomology. We're going to see this in the next few lectures. And the third thing, and this is, I don't know, let me say subtle, is I used level gamma 0p. I really was at level gamma 0p so that I could access this WR bar up. And the action of UP. Okay, the action of this thing. I mean, if you take the naive decomposition of these double processes, you add in the extra object you get for the p-adic Hecke operators, the WR bar would not have been stable. And I would have run into an argument in step 2. I would run into an issue in step 2. Okay.
He's saying that all your K's, they're all level 11. They're all on gamma naught 11.
So they're all on level gamma 011, except that what you're going to end up, if you really carry out the analysis further, you're going to end up finding out that they arise from level 1 eigenform by degeneration. And that's why I wrote F12 as delta. Like technically the eigensystem I construct are at level 11, like Raghuram was saying. But I know what the U11 eigenvalue is, it is a unit. And that can't happen for a new form at level 11. So it has to have come from a degeneration. Yeah. So there's more to do there. And we'll get into this maybe when we talk about p-adic function. I'm not quite sure where the plan is going to go. So are there any other questions? I have an agenda, but I'm also happy to just answer questions about this argument. What I want to do for the last 20 minutes then, 15 minutes, is give you an idea what the eigenvariety is. And however imprecise it becomes and however much I leave left, we dealt with, I'll pick up in the third lecture. Because I didn't explain part 3. All I did was produce congruences between lots of eigenforms at this point. And part 3 is a different story. Part 3 is a much more serious question that requires analysis. There's no analysis on the board. There's only mod 11, mod 11, mod 11, mod, right? Let's talk about moving weights. I want to kind of go through 1, 2, and 3. So how do you move weights? You move weights by constructing the p-adic weight space. So this already showed up in Miladin's talk. It kind of showed up in my talk first, and then it showed up in Miladin's talk even more explicitly. And so for the third time now I bring it up. So definition, what's a p-adic weight? A p-adic weight is a continuous character on DP cross. Continuous. And here, L over QP is some finite extension. Actually, by continuity, it'll land inside some compact something of L cross, and it'll land inside kind of the unit in L cross automatically. But we tend to use the field no matter what. What do these things look like? So 80 kappa, P is not 2. Is determined by what? So it's determined by its action on the torsion part of DP cross. For the P minus first root of unity, and that action always has to be raising to a power. Okay, so this is x, so to x to the j. for some j between 0 and p minus 2. Then ZP cross doesn't just have torsion, it also has a procyclic part. And so I can define W kappa to be kappa of 1 plus p minus 1. So this here, this generates 1 plus p ZP as a topological group. 1 plus p is very close to 1. Kappa is a continuous character. That means that its value on 1 plus p is also close to 1. And so W kappa lies in the set of W, I guess, in L of norm p-adic absolute value less than 1. And conversely, given any p-adic number in L whose norm is less than 1, I can construct a kappa that's a continuous character whose value on 1 plus p will satisfy this property. So what does that mean? That means that this base of continuous characters of DB cross is p minus 1 copy of an open p-adic disk. Okay. For example, let me just make this point. So kappa of x is x to the n, within an integer, then W kappa is 1 plus p to the n minus 1 is np plus n to 2p squared, and so on. And you can be really explicit about these kinds of things. And the point I want to make is that the p-adic topology on the exponent n is the p-adic topology on W. If n and n prime are close p-adically, then the W's are also close p-adically because you're going to see it from this formula. So this isn't like a random decomposition in the open disk. It's preserving the p-adic topology on the integers. Good. I skipped saying what happens for GLN because I'll have to bring it up later. And I can say aloud for GLN, you use what we've seen in the Jira talk. You take continuous characters on the n on the diagonal matrix over ZP. And here I know that n is 2, but I only took 1 copy. But that's because I made a twist from the very beginning of the story. There's no determinants in my symmetric polymers. So that's something that you tend to do with GL3 that for various reasons you decide not to do. Anyway, oh, this is the theorem I want to prove. Okay, maybe I don't take that. Yeah, no, so now what I'm going to do, I'm going to do something related to the distributions that we saw in Milan's talk. Actually, and we saw this idea. I wish I understood Archimedean questions about representation theory better, so that I could understand how the following relates to what was in Ragarov's talk. Maybe someone can explain it to me. So what I'm going to do is I'm going to take distribution cohomology. That's not some special thing. I mean, I'm just going to plug the distribution models into the cohomology. There's not some special cohomology called distribution cohomology. And this idea really is due to Glenn Stevens. So I had Peter prove this theorem, but he didn't prove it this way. So he would not have constructed these kinds of things. In any case, what we have are the distributions on ZP, the locally analytic ones. On ZP. And one of these guys is we kind of write mu. And mu, if it knows how to do anything, it knows how to be a linear form on locally analytic functions. So I'm not saying that it's exactly the linear forms on locally analytic functions, because there was a discussion about that and the kind of subtle continuity issues. But it knows how to be a linear form. Like it's inside the linear forms. And one thing we didn't see, so I fixed kappa of p-adic waves. What we didn't see last time is that there's actions on this object. So you can do things to distributions. You can take a 2x2 matrix, A, B, C, D, and you can act with a weight kappa action on a distribution. So that needs to be another distribution, where I need to plug in a locally analytic function. And then I need to give you a formula. And what you're going to do is you're going to take the distribution. And you're going to consider the following function. The function that says x, kappa of cx plus b, half of ax plus b over cx plus b. So as a function, the way I've written it, I need to justify that it's locally analytic. And to do that, I need to even tell you what I'm plugging in here. Right? Kappa is a character on ZP cross. X is a variable in ZP. It doesn't really matter what C is on it. D needs to be a unit. Okay? Sorry, C is got to be divisible by P is what I meant to say. So this is a left action of delta 0 P. I'm going to put an X there for units. And this is your like third monoid or something that I've written down, the ABCDs that are in M2 of ZP intersect GL2 plus GP such that C is divisible by P. So that's the condition I had before when I was analyzing everything. That'll make this divisible by P. And then I need to make D a p-adic unit to make sense of that.
GL2 plus.
We don't need a plus because you're saying that this is equals. No.
M2 of ZP intersect GL2 plus Q.
Oh, but you don't need this.
I don't need it for what purpose?
You don't need the plus.
I don't know what you mean. I don't need it for what purpose? I put it there.
I'm saying,
If I erase the plus, it's the same thing.
you don't have to intersect with something in Q. You can put like QP.
Yeah, I could put something different
You
here.
put GL2 plus QP because it might be needed later. That's what I'm saying.
Okay. It's a left action of this monoid. There is one thing, so Melania did mention it's half vector x is only a continuous character. So for this to make sense, I need to be integrating a locally analytic function here. And so there's a separate fact you need to know that this function is locally analytic in x. And that's something Melania mentioned as an exercise in his lecture. But given that, then this is a locally analytic function, then I can plug it into my distribution. For definition, d kappa is the distribution on ZP with this action. Okay, so let me just mention. In the beginning of the talk, I'm talking about these algebraic representations. And there's one of them for each integer, r. And they're different. They have different dimensions, right? The dimension of my MR was r plus 1. This is a completely different way of constructing things. There's one object, the distributions, and I'm varying the action on them. These are infinite dimensional objects even. They can't be, it's not like the dimensions of the symmetric tolerant where they're really varying and it makes them hard to compare. Kappa by kappa, I have the same p-adic Crochet space, as they say. And it's really, I mean, it's amazing what all the tension in these finite dimensional representations is completely released when you leave the world of finite dimensional vector spaces and you go to a single molecule where you're varying the action. Okay. Now this is the part that's connected somehow to Rodderon. So in Rodderon's talk, there is on this board this exact sequence involving some sort of induction, which this thing is very close to, by the way, whose quotient was this MRs. So the p-adic version of that. Okay, so that's the key result on the action. This is the following proposition. So I take an magnetic wave and algebraic an R power map, where R is at least 0 is an integer. Then there's a map that I call the integration map. I don't think everyone calls it this, from the distribution onto MR. Well, let me tell you exactly what it is again. MR, which if you've forgotten is the symmetric Rth power of Z squared onto, and it's delta 0 cross of P equivariant. And the formula I can even tell you. IR mu, so mu is the distribution. I need to give you a polynomial, and what you do, if you take a polynomial, okay, that's a big X, that's the one for the symmetric power, and then there's a little x, that's the one on ZP, and then there's a y, and then you need a polynomial in R, and now x is a variable in ZP, so you can integrate that variable with respect to the distribution, and you put a mu there. Now, if you want, you could expand it and be really precise about it. It's R to J. You take what's called the J moment. These are important for these questions of admissibility. A lot of talk. X to the J, Y to the R minus J. That's what this thing is. And given the formulas I've given you, you really have the capacity to check this proposition. Okay. So these distribution modules with the various weight kappa are not actually different. They contain different finite dimensional quotients for this action of this monoid. But this monoid contains all the important matrices for defining the Hecke operators. It contains P001 and it contains L001 for the various L's. And then so the main consequence is that IR induces a map for the algebra of unratified Hecke operators and the UP action from the H1 of Y gamma 0 P D kappa to the H1 of Y's gamma 0 P MR, and maybe there's a plus minus. Maybe you could localize in the Hecke action before you do anything else, but you don't need to for that statement to be true. And maybe you could use one of these fancier interior cohomologies or something like that. But again, just for the statement, it doesn't really matter.
But I think the arrow is going different from the way that I would expect. Like it's not contravariant.
It's in the coefficients. The map is in the coefficients. Cohomology is going the right way in the coefficients. Because yeah, a coefficient is a linear form. I'm just composing with this map. Yeah, and there's also, by the way, there's a kernel to that map IR. That's another one of the D kappas. Okay, and that's somehow related to the discrete series, I guess. I mean, I don't really. And a long time since I saw that field through Armstrong, and so I was really shocked when I saw you write on that AX sequence this morning. Okay, and so now let me just say the eigenvariety. So this is my attempt at stating a theorem that somewhat describes what the eigenvariety is. And I end by just stating the theorem and giving no indication of how these arguments really work. We'll see what I decide to do as we move on. There. I actually make sure I write it the way I want to. So what I'm going to do is I'm going to fix P, which is an element in the cohomology, a little gamma 0 P, with coefficients in MR. I fix the plus minus, and I'm going to assume that this is an eigenclass for all the Hecke operators away from P and the Hecke operator at P. Then part one, so part one is subject to the normalizations, and actually that's the one normalization I haven't checked in all of these formulas to check whether part one is exactly true or whether it's true to a twist. So part one should tell you that the UP action on phi is alpha on phi for some alpha whose p-adic order is between 0 and r plus 1, and in particular it's non-zero. Okay, and this is the statement about the classical homology, L gamma 0 p. Part two is that there exists a picture that looks something like this. So inside, let me see. You have W, this is the p-adic weight space. Inside there, you have some open neighborhood. So remember, the p-adic weight space is just a bunch of open disks. So I have some small open neighborhood that contains the character x to the r. Okay, and I have some object above it, a rigid analytic space in here that is some kind of p-adic disk, some closed p-adic disk that's having finite on my open neighborhood. And up here I have a point V phi that's going to map down to XR. Okay, so there's some picture, some geometric picture like this, a p-adic space over a p-adic space mapping finite to 1. And there's a character on the Hecke algebra valued in the ring of functions on V. So V has a structure T and there's functions on it. There's a way of taking a Hecke operator and generating a function. And then subset, so there's the data of this finite map. This, I already have 1 and 2, so A. If V is in V, then the H1 at level gamma 0 p of the D, I need a notation, all right, kappa for the map that sends V to a point in weight space. I look at the D kappa of V, I take a point in V, I take its weight. And I take the eigenspace for the psi V action. So I take psi and I evaluate it at V. This is non-zero. So every point in V gives rise to an eigenclass inside the distribution value homology. Part B is that when V is V phi, then, well, psi V phi is the eigensystem. P, right? P is an eigenclass that has eigenvalues, and I'm interpolating that one. And part C is that if R prime is, I think, bigger than or equal to R, and x to the R prime is also in my open set U, and V prime is a point over R prime, then V prime also arises from a classical homology class. And V prime maps to R prime under kappa, x to the R prime. Then there is a P prime associated with V prime in the H1. And I'm running out of space here. Let me write MR prime. Okay. And hang on, I'm at the end of my talk, so then you can ask a question. So just to say for the third part, what I'm saying one more time is that at R, I have a point in this space V that maps down here and arises from this classical homology class. And also at any R prime that's larger than R and also lying in my space. So this space might be a very tiny ball, but it will contain weights arbitrarily close to R p-adic, so very large weights. And they will also all give rise to classical homology classes in the space of varying homology classes. Or varying eigensystems. I want to be really careful about that. I'm varying only the eigensystem. Okay, so that's all I'm going to say for my lecture today, and we'll see where we go in the next couple of days. Thank you for your attention. Now, your question below.
That's good.
What?
You want to read, but I can ask you.
Oh, no, but you can't read it? Which one?
You said something about people that do right, so. You don't need like a psi of UP. You said something already, but you didn't write it. You said something like psi of UP, it's in OV star. Or you didn't-
So all I'm asserting. I'm not asserting some kind of uniqueness or anything. All I'm asserting is the existence of these things. And then you would approve the statement and you might add more things in it. And so in fact, let me add that statement because here I made some point about saying that UP acts non-zero in the eigenclass. In fact, UP will act non-zeroly on the entire family.
What you wrote there is equivalent to alpha null zero, right?
This is not quite equivalent, because I'm also bounding it, but sort of.
Cannot be more than that without being zero, right?
Yeah, you're right. You're right. But let me just write this in.
Oh, because your statement is there exists U and B. Okay.
Yeah,
Okay.
I'm not making some statement about how to prove this or anything, but in fact, psi of UP is gonna be non-vanishing. But it's not vanishing at this point. It's not vanishing at D5, so you can almost kind of straight to make it non-vanishing, even if you didn't know that from the construction. To construct these things, you actually do need to really be careful about that kind of thing. And that was my third point about controlling the UP operator. This is something that I want to talk about more as we go on. Yeah,
That map IR.
yeah.
DK. Is there a GLN version of this map?
The D doesn't have a GLN action. So there is in some sense a version of this. So I said that the D is almost it's related to an induction somehow. And this might come up depending on how far Mladen and I move into GLN questions. But the induction I'm referring to is an induction from the intersection of a Borel with the Iwahori up to the Iwahori. So ZP here is related to the unipotent inside GL2. It's like the ZP points of that. So there's like an Iwahori induction that's going on with this distribution. Instead, what you could do is you could realize these symmetric powers themselves as inductions of algebraic characters, and kind of taking algebraic functions inside inductions. And then you can take a GLN induction. You can just take locally analytic functions inside an induction from E to GLN if you want. And there's still a surjective map like this, and there's kind of a whole BGG resolution at that level. That's not kind of, and that's kind of like what this is, but it's not exact. I would say that's the GLN version, though, if I had to answer your question. Any more questions?
You said something about the kernel of IR is also another decay.
Yeah.
What is that? Take your IR over there.
Yeah. So actually, it'll induce an exact sequence that looks like MR is the quotient. And then you have D, let me call it DR instead of D kappa. And then
Minus R.
D minus R, thank you. Like this, and there's a twist, so there's a determinant. Maybe there's a one-dimensional twist in there. And so, yeah, that's it. Yeah, so, and that's a whole story about that.
Actually, the twist will be exactly by the slope that you don't want, like R+1 or something.
Yeah, maybe it's the determinant of R+1. Yeah, so there's another distribution model. And so cohomology classes in this give rise to kind of weight negative R things in my families if they lie, if they don't quite lie in the same weight distance, so they'll kind of be near each other.
So the GL2R, that R is real numbers, the short exact sequence where I put down. For GL2C, there is a similar finite dimensional and induced quotients down to a finite dimensional, and the kernel is the sort of analog of discrete series, not discrete series, of course. But that itself is an induced representation. It's some, I don't know, there's something very reminiscent of what happens to GL2C, but not so much to GL. So what's a good reference? Give some references.
So,
For,
so for this kind of thing, I think already unfortunately, a lot of the early papers in the theory were never published. So the best reference for all of what I kind of said just now, I think, is the Eigen book, which is a book that was recently published by Galois, who also sadly passed away 6 weeks ago or so, I think. He was my advisor at Brandeis, and he taught a course on eigenvarieties and p-adic functions. And I certainly got this lecture in my head from that course. Like, I don't think I referenced the book when I was writing this because I kind of was doing it off the top of my head, but the best reference for this kind of thing, especially in checking all these details, is probably the item book by Bergdall, in which he's synthesizing a lot of the work of Glenn Stevens. It's fair to say, I mean, Joel even writes this in his books and in his papers, how much Glenn Stevens' work influenced him in thinking about these things. But Glenn never published papers on the topic. He kind of wrote them, and then people used them, and eventually they had to be published by someone. And yeah, and you'll see a much more sophisticated version of this statement. Maybe I'll bring this up at the beginning of next lecture, so that it's really something you could put in your pocket and take somewhere else. It's kind of probably hard to use the way I wrote it. Yeah.
So something Milan mentioned, wait, so if without the slope or if the valuation of this alpha is bigger than r+1, then you were saying it was automatically 0?
Well, actually there can't be anything else. Like
It's more, okay, so when you're at the classical point of weight K, case r+2, I guess.
Oh, right, so
I mean, just like look, what can be the slope like of a modular form of weight K, you look at the roots of the Hecke polynomial.
I see.
So if it's unramified, like the sum of the evaluation is K-1, so like they have to be between 0 and K-1. And then if it's Steinberg, it's like K/2, K-2/2.
Yeah.
If it's principal series, it's like K-.
Yeah,
But anyway, it's between 0 and K in all cases. And
yeah.
so, and okay, so what's not written on the board, maybe it's written, but somehow not directed. That when you do this family, I mean, because it's a continuous function, the valuation will stay constant in a neighborhood. So like whatever's true at the initial point will take you small enough so it stays constant.
Yeah, so I always had I assume there exists something that makes essentially an analytic family of Hecke eigensystems. And there's a further thing you have to do if you want to prove it, which is to realize that that analytic family is not going to just cut up random eigenclasses, but eigenclasses where the norm of the UP operator is exactly the norm of the original alpha that you're starting from, the original eigenvalue of UP. You cannot prove the theorem without realizing you need to do that. But you can state the theorem without saying it. And I thought we were going to talk more about these alphas anyways, and so it was worth.
It's a challenge to do families when alpha is 0. What is not possible? I don't remember.
I've heard there's some theorems claiming it's not possible.
Periodically do such things, and people periodically do this, but it's impossible. I mean, I don't remember what's the numerical data showing. When alpha is 0. Like maybe some of you guys can look into this.
Anyways, the first statement is actually something like at the exercise session, I or someone could explain. Like it's really a kind of analysis of modular forms in these two linear schemas. The gamma of 2 example that Ragaram was talking about in his very first lecture on the delta function. But yeah, sorry that caused some confusion. That's not supposed to be the obscure point of everything. There's plenty of other things to worry about. Maybe we can take an extra long break. I mean, yeah.
Certainly.
So we kind of went on a little bit here. Oh, wait, no, we're done.
Yeah.
Oh, we're done for the day. Ah, okay.
Well, there's
Even better. We have all of time, but we don't have another lights.
no more lectures today.
Yeah, that's what I meant. I didn't want to come back on in 4 minutes or 15 minutes, but. All right, thank you again for your attention. Oh, no, you don't.
So you heard that there were some theories that it's not false.
So Andrea Ponti told me he was working on a theorem basically. That